Today we're going to be hearing from Nate Pallo on electrically thin approach to switching cell design for flying capacitor multi-level converters. He's got a paper that he's preparing for, so let's see what he has to say.
Great. So again, yes, I'm Nate Pallo. Thanks, Nate, for the introduction. This is on electrically thin design for flying capacitor multi-level converters. And to begin, I'll start with the motivation for both flying capacitor and wide bandgap designs. By talking about electric aircraft, NASA sees power-dense inverter technologies as an enabling technology for future electric aircraft. This means we have to have both high specific power and high efficiency for these vehicles. And ARPA-E also sees high efficiency and fast charging as a requirement for electric cars. And that also means that for onboard charging, so that we can actually have these converters in the vehicle, we need to make sure they don't take up too much space. So flying capacitor multi-level topology shows a promising solution to these needs, and wide bandgap devices with the promises of faster switching speeds, low losses, and generally smaller form factors could help further this goal. So today I'll be talking about wide bandgap devices as applied to flying capacitor multi-level converters and an electrically thin approach to mitigating the inductance of these circuit assemblies to help better obtain the promises of wide bandgap. This electrically thin approach will be explained through both the simulation effort to verify that the design would work, as well as experimental tests that prove the simulation indeed indicated performance gains. And I will summarize with the key results of this study as well as next steps. So to begin, I want to talk about the advantages of the flying capacitor multi-level technology. Everyone in this group is pretty well aware of that already, but really I want to focus on the high effective frequency in this case. And this effective frequency is determined by the number of levels, n-1, times the switching frequency of each individual transistor. In the case I'm showing, this is a 9-level example, which I'll be basing a lot of this discussion on throughout the talk. We can see that the switching frequency seen at both the input and output inductors is effectively 8 times the switching frequency of a single switch. And what this means is that combining this high output frequency, high effective frequency, with multi-level operation, we need less filter inductance and capacitance to convert the output voltage waveform, shown in blue, to a very nice sinusoid for inverter operation. In these converters, the flying capacitors store most of the converter energy, and from what we've seen in previous work, increasing the frequency allows us to decrease the required flying capacitance for a given power level, indicated by the current and the direct voltage in this case, for a given ripple spec, the alpha in the equation. GaNFETs make a seemingly obvious choice in this case because of their very high scoring figure of merit. We can switch them quite fast due to their low output capacitance and gate charge, and we can push a lot of power through them efficiently due to their low RDS on. Additionally, they typically only require a low threshold voltage to turn on, and this is convenient because we can drive them with logic supplies we already have present on our converter. And in many cases, especially with the chip scale devices I'll be discussing in this study, we can find them in a very small form factor. So combining that with the low losses really enables power dense designs. But before we go too much into the advantages of the devices themselves, we have to discuss how they're actually implemented in a converter. And in this case, I'm showing a 9-level flying capacitor multi-level converter. I won't go too much into the operation other than we see that these devices represented by switch 5A and B are idealized in this case, except for their output capacitance and parasitic inductances that arise from the circuit they're actually assembled into. Again, without going into too much detail of the operation of the converter, all we really need to know here is that switch A and switch B are going to be complementary. So when switch 5B on the bottom is off, that means the output capacitance is charged. During commutation, when S5B turns on and S5A turns off, they're complementary switches, we see a discharge of the output capacitance on S5B and a charge of the output capacitance on S5A, much like you would see in a half bridge. This commutation excites the resonance between these output capacitances and the parasitic inductances in the assembled board. So what we really see is that the PCB traces are going to limit the effective gains from wide bandgap technologies. The series inductance is going to reduce how fast we can actually slew these devices, while we'll also have to worry about overshoot and ringing. And this can be illustrated through this figure. If we slow down the turn-on transition of this bottom FET using the previous example, we can slow the rise time of the voltage across the upper FET, the complementary FET. And we see that does indeed produce a turn-on waveform with very low overshoot. However, this slow rise time corresponds to a high overlap loss. And so this will be a potentially lossier converter implementation. We could use a really small gate resistance and have a very fast rise time, but that will end up exciting the resonant tank between COSS and the parasitic inductance. And we could end up having detrimental overshoot as well as EMI concerns with the enhanced ringing. So our motivation is threefold. We want to decrease these parasitic inductances so we can have a much faster slew rate. We want to reduce that peak overshoot so that we stress our devices less. And we want to damp the ringing so we can have less of an EMI concern. So at this point, I'll discuss how do we actually go about reducing that inductance. In previous designs, this has really meant achieving very tight magnetic coupling between the complementary FETs. These designs have used a lateral layout where the complementary FETs, the A and B FETs, are on the same side of the PCB, and have employed local bypass capacitors on the same side of the complementary FETs, so that we, in effect, get a much lower impedance between the two FETs in parallel with the parasitic inductance that would be going to a bulk flying capacitance on the bottom side of the board. However, for high voltage designs, this lateral layout is less desirable. We need to obtain high standoff voltage in these cases, and we don't necessarily want to have that distributed through the air or through creepage along the PCB itself. So in these designs, we employ a vertical layout where complementary FETs are on the opposite side, and the voltage standoff is then taken care of by the PCB itself. In this case, the complementary FETs and associated flying capacitance will be on the bottom side of the full converter instead of on the same side. In these designs, we've also seen how parallel paths from adjacent switching cells can effectively reduce the parasitic inductance. Unfortunately, in these designs, we see the cross-sectional area through the PCB still contributes to the inductance, where the inductance is proportional to the cross-sectional area. This design was from this previous paper earlier this year, and I'm going to refer to it as the base comparison case for vertical designs going forward as ISC 0. And in this case, as I was mentioning, this parasitic inductance is really going to accumulate through the connection between the switching cells on the top and the bottom side. So how can we reduce this area? Well, we could, of course, make the device mechanically thin, and I show that being done through shrinking the actual stack up of the switching cell. The switching cell contains the flying capacitors and the transistor. In addition, we can tighten where the pads mate with the motherboard of the main converter so that we can squeeze that area a little tighter. But in shrinking the mechanical thickness of these switching cells, we end up starting to have to worry about mechanical integrity, not just in terms of how do we actually reflow this. There's going to be much more bend in the board as we heat it, as we work with it. But once we assemble these to the board, that will create issues with component height variation from that deformation. So perhaps instead of making it mechanically thin, we make it electrically thin. We can use internal layers on the switching cell daughter boards and blind and buried vias to ensure that our current only traces out the minimum path necessary to get to the capacitors and then back towards the center of the board where it goes through to the bottom PCB to the complementary FET. And we can see this can be obtained using more layers, but in the same thickness of the overall stack up of the PCB. So visually, I'm showing this as a similar, actually greater reduction in the commutation loop area. So given this idea that we can shrink the cross-sectional area and therefore the parasitic inductance, we wanted to go ahead and test this without making a full board run, see what this performs like in simulation. And this was done in ANSYS Q3D. We took the solid model, in this case I'm showing of the ISC0 design, and did a 2-branch simulation. So just 2 of these paths, not considering the parallel paths from adjacent switching cells. We simulated the switching cell board, the converter motherboard that we need our commutation current to circulate through, and then a bottom switching cell, the complementary switching cell on the bottom side of the PCB. Once this was simulated in FEA in Q3D, we pulled this model into Simplorer, which essentially allowed us to combine the other devices, such as the SPICE models for the GaN FETs, as well as S-parameter models for the flying capacitors we want to use, and see how the whole system behaves electrically given the RLC models of our actual circuit implementation. So to simplify what this design is actually doing, we created an effective circuit that has a bias voltage, represented as the voltage normally across the flying capacitor, as well as a bias resistance. In this case, the bias resistance allows the top switch to be normally on unless we commutate the bottom switch. So we'll be driving this SB to actually trigger this transient. This ensures also that the COSS of the bottom switch is going to be charged while SB is not conducting. To do the transient, we toggle SB on so that we effectively observe how this charge will commutate to the complementary switch. By turning this one on, switch SA will automatically turn off, and then we can observe the VDS across that upper switch to see how much overshoot we get from the ringing in the modeled circuit as well as the COSS from the SPICE models. Overshoot and ringing frequency were chosen to be the performance metrics in this case. Lower parasitic inductance means that we'll have less overshoot at a higher frequency. So for the actual transient simulation, we compared it with a simulation of ISC0 from the previous design, as well as a mechanically thin version, as described previously, and an electrically thin variant. In this simulation, we see that the overshoot was reduced by 1.5x with the electrically thin switching cell. The mechanically thin version was somewhere in between. We notice in this case there's quite a bit of ringing. Again, this is just a simulation. We aren't trying to fully resolve the entire converter performance. We just want to see what the difference is going to be like with this change in the electrical connectivity. So the key thing we're focusing on here is that we see that we can get a 1.2x gain by making this layout configuration. To find the actual inductance value, we did a transient sweep, an AC analysis with a frequency sweep. We effectively shorted out the bottom FET and put a test capacitance with an AC source on the other FET, treating this as a Thevenin model. The reason we do this is we can account for any mutual inductances that were simulated from the finite element analysis. And for the two-branch analysis, which was the transient simulation just done before, we can see that we get greater than a 2x reduction in the parasitic inductance. If we do take the extra step for a four-branch to consider the adjacent switching cells, we can see that can be further improved. So the simulation is fine, but we wanted to see how will this actually perform on the physical hardware and how well do these gains line up. So we actually fabricated a mechanically thin version and an electrically thin version of these switching cells. And we tested the four-branch configurations, so that would be considering adjacent switching cells, on the main board that will eventually be used as the converter platform. The four-branch configuration was used in this case because that'll be particularly relevant for the actual converter implementation. And again, the complementary switching cells are on the opposite side of the converter in this case. We drove these test circuits with the same effective experimental circuit as described in the simulation, where the bias was in this case 100 volts, and the control of the bottom FET was done through a trigger source, a function generator. And then we observed the ringing across the drain source of the upper FET, as in the simulation. In this case, we see significantly more damping than the simulated results. But the big thing I want to point out here is the gain we get from the reduced overshoot. Again, this is the four-branch simulation, and so that we expected to have slightly better performance, slightly lower inductance. So we actually see a 1.4x gain here. We also see the frequency does indeed shift from 89.3 to 125 megahertz. So that does also indicate that our parasitic inductance did indeed shrink. To compare this with the simulation, again, there's less ringing, but the decrease in the relative overshoot does agree fairly well. And surprisingly, the mechanically thin variant performs less than we had expected from the simulation. The electrically thin design, again, I mentioned this uses internal layers with blind and buried vias. This can be a somewhat more complicated process to manufacture and somewhat more expensive. In this case, about a 3x increase in cost per board. So what would it look like if we used only buried vias? Those are a little bit easier to put together. Well, rather than doing a full manufacturing spin on this hardware, we decided to use 3D printing to quickly evaluate this new topology. And this is promising because in the future, this could allow us to just 3D print individual variants and test it that way. So on the same converter, I call out the 3D printed switching cell, and we want to see how that compares to the electrically thin cell. This 3D printed cell is representative of just using buried vias alone, not the blind vias. In this case, we see the results were relatively comparable to the actual full electrically thin with blind and buried vias. The electrically thin shown in the green plot with the 3D printed shown in the orange. However, we also notice from this plot that the decay of the 3D printed switching cell, as well as the slightly reduced rise time, seem to indicate that these circuits might have an additional higher resistance or other characteristics associated with them from the 3D printing process. So perhaps what we've learned from this is that the comparison shouldn't be between 3D printed and professionally manufactured circuits alone. Again, I showed on the previous slide, this is only tested with a one branch. So that's to say only using 2 of the capacitors on the switching cell because there was a steep learning curve in handling these devices. So to sum up what we accomplished through the study, we demonstrated an electrically thin approach to switching cell design, and we've shown how that we can leverage internal layers as well as blind and buried vias to reduce the parasitic inductance associated with the commutation loop in these designs. The simulation and the experiment fairly well matched up, and indeed, while I mentioned a 1.2x for a 2-branch simulation, 1.4x for the 4-branch, A subsequent run of a 4-branch simulation showed that the improvement actually exactly matched. So that's reassuring that we can use these simulations moving forward in future designs. 3D printed circuits, we do think they will be allowing us to rapidly prototype new design variations that we can use to validate simulations. However, they might not be best directly compared with traditionally manufactured PCBs. At the very least, we gain knowledge on handling and assembly of these devices. And a full DC to AC converter using these electrically thin switching cells will be demonstrated at APEC early next year. And we're targeting a 20 kilowatt output power of this inverter with low harmonic distortion, with a predicted power density of upwards of 30 kilowatts per kilogram and over 98.5% efficiency. I would like to thank our sponsors at NASA, both through the cooperative agreement as well as the Center for the Power Optimization of Electrothermal Systems, as well as collaborators at Arkansas for initial guidance on the Q3D setup, and Alex and Fathom Studios for the donated 3D printed switching cells. So thank you for your time, and I'll take any questions. Read.
I'm a little confused on what you mean by 1.2x and 1.4x.
Yes.
I'm a little confused on that.
Yes, that's a good point. So to clarify, I was using the relative change in overshoot. So what I'm saying is that this overshoot is around 98% change, like 98% over this nominal value of 100 volts. So it settles, once it rises, it'll settle to that voltage, to the V bias. It's a comparison between the overshoot of the two designs.
Okay. Do you think that the 3 times more expensive is worth this change in overshoot in general?
That's a good question. I think I would much rather see how well buried via only application works, since that will be significantly cheaper. If it is indeed as comparable as this design seems to indicate, then we can perhaps reduce that cost a little bit. The efficiency gain would have to be considered at the system level, whether it makes sense in the full converter to employ this, because that's going to change how fast we can switch the overall converter, and that folds into the sizing of the input and output inductors. But I think that's something that we will still need to study. Yeah. Yes.
I'm curious, in your experimental test setup here, do you have a biased current that you're switching between?
A bias current. So in this case, there's a relatively high resistance R bias, about 200 kilo ohms. So that's really just meant to ensure that there's some amount of current trickling through this diode so that this COSS is discharged and so that this COSS is charged.
Do you foresee there being a difference in the overshoot response compared to a real or a full converter where you would actually, those transistors would see 10 amps through or something? Or do you think, have you looked at how good replicates this transient setup compared to what you see in a real converter?
I think that's a good question, because it also indicates that the full converter isn't going to be a single switching cell. We're going to have current paths and additional inductances on either side. I think in this case we have made some simplifications to make the test easier to conduct, but that would be something to look at going forward. Great. Well, if there are no further questions, I was hoping to quickly show people how you might be able to do this yourself, set up the simulation and everything, since that's what's always missing from these talks. So, all right. I'll move on to that, and we'll see if this can work. Kevin, I'm going to... Yes. Let's see if... Oh, you can put it on the screen too. I guess that'd be fine.
Did you just have PC?
Yeah, it's the workstation one, so. And can you bring the other screen down?
I think you got to do it.
Ah, yeah. All right, can you make me a presenter too?
Yeah. Did you request? I think you have to request.
Yep. Okay.
Sure. You know how to do it, but I don't see anything.
Okay.
There you go.
Great.
It just says currently presented. So
Yep.
you automatically got it.
It looks like it's doing it. All right, the first step in this process is to get the files from your schematic editor or your EDA. I'm going to show KiCad. Don't interpret this as an endorsement per se, but this is a way we can make this work. So this is the PCB Layout version of KiCad. Right now I'm showing just the top layer and bottom copper. This is the switching cells that we just did. So the electrically thin with the tighter pads on the bottom. And to get stuff out of this program, we use plot. There we go. And instead of doing the normal Gerber, we'll actually go to DXF. We're going to convert this to the mechanical domain. And just for now, I'm going to do top copper, bottom copper, and edge cuts, which is the board outline in this case. Click plot. It creates them in whatever folder you're working out of. And we can open that in a mechanical editing program, such as SolidWorks, to generate our 3D models. Q3D has 3D in the name. So we want to get this PCB into 3D. There may be an easier way to go from circuit design into the mechanical domain. Andrew's already played around with some of this stuff using SI Wave, where it imports the board files and it's able to do some stack up stuff. That is possibly useful in not only maybe being a little easier or just different. I imagine how it captures the vias and different pads. There's probably some sort of simplification ANSYS can do, knowing the geometry is a specific shape, instead of having to try and mesh over cylinders, which would be what you would do in SolidWorks. In any sense, this is the way I was more or less taught through discussion with our friends at Arkansas. Just do it in SolidWorks. Don't even draw the circuit beforehand if you don't need to. But I'll show you how to get those DXF files by selecting a plane that we're going to work in. I'm going to choose the front plane. Actually, no, I'll choose the top plane. It doesn't really matter, but you can see there's X, Y, Z associated with it. So the Y is going to be normal to the top plane in this case. And I'll go to Insert, DXF. I'll do edge cuts first. That's our board outline. Oh, actually, this isn't quite right. A step I skipped was in here. I chose where my origin was, and I said I wanted it in the middle of the board. Thinking about this stuff in advance, how your simulation, how your models are going to assemble in terms of related spatial origins can save you a lot of time. I don't have too much of a good example for why that's useful here, other than just saying that it is. Somewhere hidden here is the tool to actually set your origin here. I forgot to mention that when you plot I checked use auxiliary axis as the origin. So that means whenever I insert my DXF, and I'll do that as a 2D sketch, make sure my units are correct, millimeters. It exports all the layers. You can uncheck them if you want, but they're just empty, so it doesn't really matter. Only one of them is going to be defined from that plot function. And you can see, because I had checked that use auxiliary origin, this is where it's going to recognize the origin of my drawing to be. So everything else looks good. This is nice because it'll create closed paths if the software didn't. And I'll click Finish. And we've got the outline of the board. Now the thing is, whenever you get any sort of output from your editing, your PCB design program, it outputs traces. Depending on how it exports them, the board outlines a certain thickness line in KiCad, and in this case, SolidWorks interpreted that as a shape instead of just a line. It's only about a difference of 2 mils, so for simplicity, I'm just going to delete the outer border. We really only need one because that's what we're going to use to create our PCB body with, using this extruded boss tool here. So I just want to quickly look up, stack up for the standard stack ups of PCBs. So for a 2-layer, using the quick turn PCB in Korea, and let's say 0.5 millimeter overall thickness. The PCB thickness is going to be 0.4.
An endorsement?
Hey, Mr. Han is pretty responsive, so. Midplane allows us to make sure it's evenly split so that we keep our origin in the dead center of the board. That may or may not be what you want to do in the end, but that's what I'm going to do here. And so we've got this nice rectangle that is our FR4. Next thing is I'm going to also select the same plane, not the top of the board, but the plane, and insert the top copper. Go through the same process. Millimeters. Oh, our origin's right in the middle. That's great. And that is what this thing looks like. All the copper, but this mess isn't that great. Like, we don't really care about that. In this case, that's all the driving circuitry. Maybe at some point that would be something you're interested in, but it'll just complicate the simulation. So I'm going to go ahead and clear all that stuff out since I'm only concerned with the commutation loop. And just join this remaining segment. Great. So those are our top copper. Yes? You said select the top plane and not the top board? Yes. It's because whenever you put the bottom plane in, if you selected the bottom part of the board, it's how it treats the normal vector. So it won't mirror it like you would. It's not like you're looking straight through the PCB. That's how it exports it. You could probably export it mirrored and it would work, but I just refer everything to that same plane. And it's fine because you can do, again, yeah, so instead of extruding from the sketch plane, which is what I did before, we'll extrude it from the top of the board. So we just say, okay, start at the top and extrude out. We see this is the copper thickness. Change it to that. So now it's going to be a nice thin thing going on here. And we want to turn off merge result. That's important as you go and design this. It'll treat everything as the same solid body if you keep merging it. But in this case, the FR4 is separate from the copper. So we need to start thinking about how that's defined. If it gets confusing as you're drawing it, you can always add nice appearances to make it look a little more accurate. I'll just quickly do, I meant to let's see. I want to get through all this. I do have a ready-made example, but I'll just do this quick. Bottom. Great. And then there's only going to be one other tricky part coming up. So again, from I would say use surface and just click the bottom of the board, but it doesn't accept that for some reason. So vertex works just fine. Again, don't merge the result. So we have the top and oops. Yeah, we have to change the extrude direction so that it's down. Yeah, top, bottom. At this point, I just want to work on the electrical connections. So I'm going to hide the PCB. And instead of putting a whole bunch of vias in, especially when the vias are like 10 mil diameter or really small, that's going to be complicated for Q3D to mesh over later on. So for this study, I did a really simple way of connecting them. And I'll create a sketch. I'll choose the bottom of the top copper layer as my sketch reference point. And I'll just be really simple about this. I'm going to draw rectangles that can extrude from the bottom to the top. Now you can, of course, be a little more careful about how you size these things and make them the same shape and equal and symmetrical. Really what I'm trying to do here is just make electrical connections from the top to the bottom with just some quick extrudes. So they're going to, in this case, extend from the sketch plane, which is the bottom of the top copper layer, and I want them to go to the top of the bottom copper layer. So that's pretty simple. Because I have hidden the PCB in the feature scope, so I want to make sure these are merged. I want the copper things to be contiguous. So I want to merge result, but under feature scope, you can tell it how it does that merging. If you have the FR4 hidden, auto select will actually work quite nicely. It won't merge everything with the FR4, so what we end up seeing is each of these are conductors, are solid bodies that are connected mechanically in like a well-defined way. And now I can show the FR4. So here's this nice PCB with connections through the layers. I'm not going to do inner layers on this one, but one thing I will point out now, and maybe you've noticed if you're already familiar with FEA, is that the volume of the FR4 overlaps with the volume of those vias, and that will pose a problem in ANSYS. But that's a problem best dealt with in ANSYS, I've found. ANSYS has a Boolean operator for doing different things with solid shapes, and I've found that's a lot easier to deal with than trying to get the corresponding shape to work right in SolidWorks. Oh, I just opened Workbench. The program is Q3D, and the other program is Simplorer. Workbench is the mechanical domain type of thing, but you can integrate the electrical so that you have all of this stuff happening under one project, and they can all kind of see each other and interact with each other, which is great if you're doing multi-physics stuff or thermal simulation or stress. So I should have shown. So to actually create a Q3D project, you would drag it from there into here. Sometimes it doesn't work the first time, so you just do it a second time. And then to actually open it, you can't click the Q3D extractor. You have to double click one of these parameters, and you can only name it from this interface. So when this is going to be rough. when I get... Is this still loading? Oh, it's still loading, I guess. Yeah, I know, more RAM. So I can simulate those vias. Actually, that would be, one other thing I did want to see is this was done with simplification of vias. I think it would be interesting to see how much trying to simulate actual vias changes the accuracy of the simulation and how much longer it takes to do that. I left it running overnight once, and it filled up the RAM and then probably about 30 gigabytes of swap on the hard drive. So, yeah. All right. This is another weird thing that happens in here, even if you have them named outside. So, like if I have descriptive names applied to these things, thin, component reference, something like that, you don't actually see it here. You only see it on the tooltip and up here. So this is kind of an annoying thing. I'm going to quickly create a new project so I can show you how to get it. Oh, maybe an asterisk on the quickly, but all right. I'll go ahead and just delete that. So under Modeler, there's an option to import our models, and you can indeed find the actual SolidWorks file. I'm not going to go through it. I thought I would. It'll act like it's importing, and then it'll give you an error. I think that's primarily because it's a new version of SolidWorks, and they probably wrote the importer for the year before. So it will import a step. I guess I should have explained. You export the step from SolidWorks, and then import it here. For those unfamiliar, a step is like a platform neutral 3D file, and it describes all the same volumes that we just created. So we have our FR4 and then the different copper layers. Now again, like I said, the vias and the FR4 are still occupying the same space. So what we want to do is select all of the stuff that we want to perform the operation on, go to Modeler, Boolean, and subtract. And they call it blank and tool parts. I think this might be a minus sign, which is a good way to remember this. You want to, from the FR4, subtract these features. You need to click this box, otherwise those features will be absorbed through this process and you actually won't have copper anymore. So this makes sure that they exist after you do this operation. They get absorbed in here. So this checking that clone allowed us to say, yes, these are all still present. FR4, I want that to be, again, green, or you can make it blue. But more importantly, I want it to be FR4. It was in my quick drop down there, but if you don't see that, you can go into the edit, type it, find it. Okay, so now it's set to FR4 as a material. This is built into ANSYS. For the remaining copper connections, let's make that, they're gold plated, so we'll make them gold. I'll call them copper. At this point, everything is mostly defined, and I think you could even do a validation check just to make sure your 3D model is okay. And knowing that I'm going to be using several of this same mechanical design, what I usually do at this point is select all of the mechanical features with the colors and materials defined and create a 3D component. And I might call this like mechanically thin ISC and save that. And then later, in a different project, I would recommend keeping the project that contains that design separate from the one you actually use. Because once you create the 3D component, it's internalized ANSYS stuff. You can't go back and edit it. You can only save over that again, at least in what I've seen. So keeping the source in its own file is a good idea. Making a separate file is just fine. I'm going to just duplicate that first project. I'll go ahead and quickly delete this. There's a lot of stuff in here for, I'll find that same 3D component. Mechanically thin, whatever. It'll put it right at the origin. Because I want to see two cells, how they interact back to back, I will actually want to change the orientation quickly so that I can stack them. An easy way to do this is to move in that direction so that the bottom copper is now seated on this axis. Unfortunately, I haven't found a good way to do that so that it only affects the y-axis, but you can go and edit the move command to quickly change that stuff. So now it's still perfectly aligned. And then the shortcut I want to make sure I show is how do I get another board right on the other side without having to do this import and shuffle around. I can select this instance of the mechanically thin, ISC, and use this duplicate around axis. And I see my z-axis is probably the one I want to duplicate around. 180 degrees means that it's actually flipped and not just mirrored. And we can verify that the coppers are indeed abutting. So we'll have a contiguous surface for our electrical simulation. Later, I can do it in that one, in this one we just had. So everything's pretty well set up mechanically. Now we just need to define our nets. Since these are all contiguous copper blocks, you can actually just do auto-identify nets. This is one of the most surprisingly functional features of this program, but I guess it's not highlighting them to show you. Oh, this is a different one. Okay. You can see that it determined these are indeed your nets because they're made out of copper. In order to actually use them, though, you need to apply pads, essentially, to each of them, which I have done here. And I took the liberty of naming them all, too. So if we're looking at this switching cell, this would be the drain, this would be the source of the top FET, and then these would be pads for the caps on the top, these would be pads for the caps on the bottom, and this is the left side, this is the right side. It's actually useful to go ahead and name all these in something that's going to make sense to you like 3 hours from now, because you'll be opening it in another program, and these are actually going to correspond to your ports. So you need to assign an excitation that'll either be a source or a sink. I can't exactly remember which is which, but for any given net, you can only have one of them. It doesn't really matter, from what I understand, how you go about picking what is your source and what is your sink. It doesn't seem to change the outcome. But I'll make this one the sink. So now we see my net has 4 ports, 1 sink and a source. If I got it messed up, which one you're only allowed to have 1 of, it'll give me an error here. Okay, yeah. So one sink, multiple sources. That's, I guess, what it wants to see. After you have all of your ports that you would want to analyze, in this case I'm only showing the capacitors, but what we would really do here is we would put a port maybe in the middle here and a port maybe in the middle here that would represent our source and our drain pads for our GAN FET. And if this were for multiple converters, we would have another port that connects to adjacent switching cells, something like that. And then add an analysis step. So in this case, add solution setup. All the defaults have seemed to be fine. If it's not fine, it'll give you an error. Solution frequency, I picked 100 megahertz because that's where I suspected the ringing was going to be. You can also set up a sweep where you can say, okay, I want you to simulate this system at 1 megahertz to 10 megahertz because maybe that's where our switching frequency is going to be, and then also simulate it at some higher number. So it'll calculate all of the RLC matrices for each frequency. The only thing I've noticed so far is that doesn't seem to impact the Simplorer simulation. Anyhow, once everything's fine, you've set up your analysis, Q3D extractor, analyze all is what you do, and it'll compute the FEA and get the RLC matrix for all of the different ports. You might want to create a Simplorer setup. Simplorer is kind of like a multi-physics SPICE. All of the devices in Simplorer have ports. You can give them inputs and outputs. In this case, what I was showing in the presentation, the circuit board actually represented a multi-port device with RLCs connected somewhere inside that black box. And I'll just quickly show how to get from the ANSYS thing into here. Well, as fast as it'll let me. It's kind of quick for getting all this down. I mean, this is recorded so that you can at least see what all the individual steps are and try and emulate that on your own. The last thing is going to be something along the lines of, I think, oh, maybe. Here we go. Simplorer circuit, add sub-circuit, Q3D dynamic component. And I think it might let me get that far. Great. Simplorer circuit, sub-circuit, Q3D dynamic component. This means that it's actually going to be linked to the Q3D simulation from before. I mentioned solving over multiple frequencies versus just one. I'm pretty sure from what I've read in the documentation, equivalent circuit only does one. State space might account for all of the others, but I think that's going to be a more complicated model that it builds. And in the dialog that pops up, really all that happens is you select the simulation that you just ran, and it gives you a nice box like this. These are all the ports I defined before, so the net name and the name of the actual port that I added, the source or sink, it doesn't really come through here because it didn't really matter. And you can connect that, like in this case, I added the EPC SPICE model. You can connect that to the different ports and run it just like you would standard SPICE simulation. So, here we go. Just quickly, this is a part where the program will crash. So, you just need to try a few times, but in here, you really just need. So I did that. This was called Q3D design something or another. Solution setup is 100 megahertz. In here, that will nominally be options you can select, and then you hit OK, and then you get this nice option. This happens a lot. There's some way of interacting with it, the right sequence of button presses and phase of the moon, and it will work. But yeah, that's in a sense how this works. So good luck. That's it.